Yeah, Assalamu alaikum wa rahmatullahi ta'ala wa barakatuh. This is the continuation of our lecture recording. So far, I think this is the first profile lecture because the first lecture was simply an overview of what embedded system is. So without wasting much time, we look at in-depth more applications of embedded system, beginning from automotive industry, where embedded system is used for engine control and in safety features like airbags and lock braking system to make this car more stable and advanced driver assistance. This includes like automatic parking assistance, like cruise control, uh, and like maybe blind spot notification. They are all included in this advanced driver assistance system. This is actually is being powered by embedded system. And if you look at consumer electronics, such as smartphones, smartwatches, smart TVs, and digital cameras, they are also powered by embedded system. Similarly, when you look at healthcare industries, there can be some devices such as pacemakers, which are used to monitor heartbeats and also to take action. If you like, you can say pacemakers are devices that regulate the heartbeat of patient with heart conditions. Insulin for diabetes and blood glucose meters. These devices can monitor patient vital signs and deliver medication. All these are application of embedded system. We also recently have application of embedded system in industrial control or automation, where you have robotics taking over the jobs of human beings. Uh, yes, such as in assembly line and material handling. In this case, they improve efficiency and also safety because human beings are no longer involved in dangerous activities. Again, recently we have seen recent development in home automation, so devices can be controlled remotely by homeowners. One can monitor one's home, even if one is away at work. And all this made possible by the embedded system. So let's go into the components of the embedded system, if you like, beginning from hardware. So, so because hardware of embedded system is not as standardized as the hardware of personal computers, so you may find different categories of embedded hardware. But in this course, we focus on the some of the essential component of hardware that can be found in most embedded systems. Uh, so, in addition to what we know about conventional hardware of computer system, hardware for embedded system have additional constraint on the following timing. Sometimes there has to be action taken within specified time. We'll see more on this memory usage because the embedded system mostly have limited memory capacity. So power consumption. In fact, some of the embedded system are powered by batteries, so we wouldn't want embedded system hardware to be consuming so much power. And reliability, because as we have been saying, some of the embedded system are safety critical, so they should be as reliable as possible. So here we depict the major components of the embedded system hardware. We call this hardware in the loop, but this is also a terminology used to describe testing of embedded system where you are testing a code in combination with real hardware physically and acting environment. Of course, I have explanation of this, but this is the physical environment. This is what makes embedded system unique because they mostly observe and action can be taken on physical environment. So what observes this environment are mostly sensors, and these sensors, when they take information, because they take them in form of analog signals, they have to be converted into digital for these computers to process. Because mostly we are dealing with digital computers. Of course, there can be analog processing computers, but in this course we focus mainly on digital embedded system. And here, this information that has been sensed from the environment and converted into digital being processed here, and then we can have display. For example, if you have like a sensor that is monitoring your tire pressure, and when the tire is deflated, this information can be displayed on the dashboard. But we can also have some information that may invoke certain actions. And in that case, we will have to have actuators here because actuators also mostly they act on analog signals, so we have to have conversion of digital signal analog for action to be taken on the environment. Say, for example, airbag need to be inflated, so the actuator that actuate airbag in this case will have to receive a signal in analog form, and that's why we have to have digital converters here. So this is a summary, but the detail is here below this the figure. So you go to read and so yes, so when we are talking about component of hardware, mostly you consider input, processing, and output. So beginning from input, we said most of the inputs are sensors. But basically, sensors can be designed for virtually every physical quantity. For example, we can have sensors for weight, velocity, acceleration, electrical current, voltage, etc. So we begin with the example of accelerator sensor, which is a sensor that measures acceleration, which is the rate of change in velocity over time. And these have their application in automotive because they are used to detect sudden changes in speed and direction, such as when the vehicle is braking or turning. This information is used to activate safety systems like airbags and stability control to avoid the car from skidding. Similarly, in aerospace, acceleration sensors are also used to detect changes in acceleration. In industrial applications, acceleration sensors are used to detect vibration in machineries. In consumer electronics, you can use it to detect what do you call it, alignment, so screen orientation, and then to take action of either flipping the screen or leaving it where it is. Other types of sensors are also image sensors, which are very important type of sensors, especially embedded system. The image sensors are basically categorized into two. The first category is called charge coupled devices, or CCDS in short, and complementary metal oxide semiconductor sensors, CMOS in short. But in both cases, they use arrays of light. As that's why if we are programming image manipulation, you realize you are dealing with arrays of pixels. And even if you are like scaling, array scaling image, you are mostly sampling those pixels that are mostly representation of light. So CCD types of sensors have been around for longer, and they are mostly more expensive, but they have higher quality image. While CMOS sensors are more generally energy efficient, and they are also often faster readout. So we see why the smartphones they use these CMOS types of images. While yeah, even in automotive they also use this kind of CMOS images. But if you look at medical images, they mostly use CCD image sensors because of the demand of high quality images. They allow for higher resolution imaging of internal organ tissue and structures. So again, well, we all know the application of biometric sensors such as fingerprints. They are also used complicated with the same technology of CMOS sensors. And in combination, CCD and CMOS can be used for face recognition. We also have other category of important sensor, which is RFID, which is radio frequency identification. Uh, this can be used to identify object animals, so, and is key enabler of this. And again, even in businesses, things are usually being tagged with this RFID, and then later information is spread. So, yes, modern cars, they are equipped with range sensors, so that the amount of, or the speed of wiper is adaptive to the amount of rainfall that are falling on the windscreen. And there are plenty type of sensors such as pressure sensors, humidity sensors, and engine controls sensors, and all event sensors. In essence, what we are saying is mostly embedded system, they use sensors as their input devices. So let's go into processing unit. Processing unit of an embedded systems can be categorized into three. One is called application specific integrated circuit, or ASICs in short. We can also have programmable processors. These are the typical processors, the ones found in conventional computing. And we can also have programmable logic. So let's begin with ASIC. So it's usually specialized microchips designed for a particular function or task. They are usually used where higher performance, low power consumption, and small form factor are critical, such as in mobile devices, network equipment, like in routers and higher end computer systems. Well, that is where performance, energy efficiency, and also we want to maintain a small size of the product. So in that case, application-specific integrated circuit is best suited. Yeah, so mostly because if we cannot have like a custom hardware component or hardware processor that can do the job, so if we can go for ASIC, we can afford it because they are very expensive. We'll see later. So they are typically developed using hardware description language, such as BHDL or Verilog, and are then synthesized into physical design using specialized software tools. What this means is the some of the processing that takes place rather than the software being bound uh, onto the processor, it's being specified, and then the hardware component is created to execute those instructions. So mostly the BHDL language is very popular in automotive domain, where if you want to design a circuit, you specify its functionality using BHDL, and then from that circuit diagram, a physical ASICs can be created. But also Verilog is also popular. So these two programming languages, they are categorized under domain-specific programming language because they are being applied into specific domain of designing hardware. Even though some think BSCL can described as a general programming, but it mostly uses hardware design. Yes, so as I hinted earlier, ASICs are very expensive to design and manufacture. So usually it's not something you go for if you want to design some few instances of embedded system. But if you want to like target mass market, because the cost is spread on the products, so then it's the best option is to ASICs. Yeah, so different from ASICs, they are also processors. Uh, yes, but processors in this case are different from conventional processors in the sense that they have been designed to be more efficient, low power, and cost effective. But they have advantage over ASICs because once you have a processor, you can design a software that can run on that processor, and you can change that software as you want. In that case, you have additional flexibility, and you can also change the behavior of the embedded system by simply writing a different type of software that runs on the processor. Yeah, well, but the embedded processor must be used in resource-aware manner. So we need to care about resources required for running the application. So they are not like our conventional processors. Furthermore, they do not need the instruction set compatible with commonly used personal computers or servers. So their instruction sets are entirely different from those in conventional personal computers or servers. Uh, so we are going to see more on this when we come to architecture of embedded system. But for now, just know that they can they can have different instruction sets. So mostly the processors have some add-on peripherals, and then they are called microcontrollers. So that's why we say a large number of processors in the embedded system are in fact microcontrollers, because the microcontrollers are small computers that are integrated into other devices and perform specific functions. What makes them microcontrollers rather than processors is the additional uh, uh, peripherals that they have. If you look at even the diagram here, you see the processor is here, but there can be and these different components are visible on these chips. Uh, they are designed to be low power, cost effective, and have small footprint. So the key features of microcontrollers is that in addition to processor, they have one chip memory for storing program and data. So in the typical processor setting, you have a processor separate memory. So instruction is usually fetched from memory and then brought into processor for execution. That's why in traditional computing, we have uh, one human architecture where we have fetches to cipher. For some embedded system, they cannot afford that latency where the memory is separate. So that's why there has to be microcontrollers where the memory itself is on the same chip processor. So again, in addition to memory, you can have additional peripherals such as the converters for converting digital to analog or analog to digital as shown in first diagram in this slide. So mostly these peripherals are used to interface with external devices such as sensors, actuators, and communication. So apart from ASICs processors, remember microcontrollers are simply specialized version of processors. So the next category is configurable logic. This term refers to the ability of a digital circuit to be configured or programmed to perform different functions or operations. So these are not ASICs per se, but they have some features of ASIC and also some flexibility of processors. We see how. So instead of maybe allow a program to be run on its processor, so we can dynamically change the behavior by simply changing the configuration of the site. So how that works is usually to configuration data. So this is desirable in when we cannot afford to go for full custom hardware chips in form of six, or because they are simply too expensive. And we don't want to go on processors because they are too slow to anything. So we may decide to go from logic. So as we said in ASICs, some of the algorithms are being implemented in the hardware rather than the software. So that's why even in figurable logic, some of the algorithms can be efficiently implemented in custom hardware, and that hardware can be configured to suit different application scenarios. It can be as almost as fast as ASIC, but in contrast to specialized purpose hardware, the form function can be changed using that. So here we are not going for fully customized ASIC, but we are going for hardware-based design that can be adapted to suit many different contexts. So they have their application in prototyping. Sometimes even if we want to design ASICs, so we may want to prototype using the configurable logic. So it can be used for experimentation. Again, as I said earlier, if the volume of application is not going to be like mass market, so we can go for logic. So configurable logic can be achieved through various technologies, including field programmable gate arrays, programmable logic devices, and application-specific circuit with programmable logic element. So what we're saying is these are the different ways of achieving configurable logic. So one way is using ASIC, but then adding some elements of recompatibility to it. Yeah, so that is the end of this lecture. So we've covered the hardware components of the embedded system, beginning from input processing. The next lecture, I'll begin discussion on the output and actuators component of the embedded system.